Perception. We've talked some about sensation, we've talked about vision and the process by which sensation gets into the brain. Now we talk about what I think is the most interesting part of the whole story, and that's perception. That's making sense of, or organizing, or finding meaning in that which we have sensed. Next slide. Here's an interesting little ditty that gets passed around by email from time to time. Take a moment to read this and then decide whether or not you think this is an example of sensation or perception. So what do you think? Is this an example of sensation or perception? The correct answer would of course be both. Sensation in the sense that you're looking at a white background with black letters on it and you're sensing those, but perception in the sense that you're making organization or making meaning out of what you're sensing here. And it's a really extreme illustration of perception, because what we're finding here is that regardless of the word order, you're still able to perceive the letters, perceive the words out of the letters. We're going to look at some interesting examples during this lecture of perception, and perception is fun in the way that it seems to allow us to have some things like optical illusions, as well as to interpret the world in a meaningful fashion. Next slide. Perception. Going back to the definition of perception that we already looked at, perception is the process of selecting and organizing and giving meaning to sensory information. What part of the environment we select to focus on, what part of information coming into our head we select to focus on, makes a difference in what we'll perceive. How we organize that sensory information coming in makes a difference in what we perceive. For example, one person may see a very slight smile on someone's face and interpret it as being a sarcastic look, whereas another person may interpret it as being a friendly look. So how we organize that sensory information is part of perception. And finally, giving meaning to sensory information. Next slide. As you take a look at this picture, this is a painting by a German painter named Albert Bierstadt. Do you see depth in the picture? Most people do see depth in the picture, and they report having seen depth for a variety of reasons. Some people will say because of the colors, that you have darker colors up front and lighter colors in the back, and that makes it appear that there's depth. Other people say that it's the size of the objects, with closer up objects like the trees being as large as mountains are in the background. Other people describe the clarity. For example, they'll say the background looks more hazy and the foreground looks more detailed, and those give some perception of depth. Depth perception is one of the more interesting perceptual abilities that our brain has. And we don't necessarily have to have a realistic picture in order to perceive depth. So for example, this picture is painted in a realistic fashion, but as we go to the next slide, we'll have a slide that's painted in a much more abstract fashion, but we also will still see depth there. Next slide. This is a painting by an artist named Mark Rothko, and it is pretty easily perceived as the same thing as the other, an image of forest that has some depth in it. And although it doesn't look nearly as realistic, we see some of the same sorts of things. We see that the colors are more vivid closer up, and in what would be the background, they're less vivid. We also see that the size of the objects helps us to recognize what's closer and what's farther away. So our brains are still able to organize and find meaning, even if the stimulus is fairly vague, like this one is. Next. Okay, here's a quick quiz for you. The sound waves coming from a flute, a clarinet, and a saxophone are translated into action potentials in your nervous system. Translating these action potentials into action potentials is called what? Second question, you pay attention to these sound waves and interpret them as music. This would be what? I hope you've recognized that the first one would be an instance of sensation. We have sound waves that are being translated into nervous system language. That's sensation. I hope you recognize the second as being perception, where we're selecting, organizing, and interpreting those sound waves and interpreting them as being music. That is perception. Next slide. Let's look at some of the principles of perception that our brain uses to organize, interpret, and find meaning in the environment. The first principle of perception is a principle called Gestalt. It's a German word, and basically it has to do with how we organize our environment. Remember, perception has to do with organizing sensory information. The Gestalt idea is that we naturally sort sensory information into larger, more organized patterns. As you look at this picture of a cube called a Necker cube, it's probably easy to recognize that there really is no cube in the picture. The picture consists entirely of round and triangular shaped pieces of blue on a white background. But even though we have multiple pieces that are separate from each other, the Gestalt principle of our perceptual organization is that we pull them together and we see them as somehow related to each other. The term for this is closure. And so what we've done here is taken unrelated pieces of blue and we've turned them into what look like whole spheres that surround a cube figure. Gestalt occurs visually, like we see in this instance, but it also occurs in auditory fashion. So, for example, you hear drum playing, and you hear guitar playing, and you hear a bass guitar playing, and you hear a person singing, and you don't interpret that as all those separate pieces. Rather, what you do is you organize each of those separate sensory pieces of information into a whole, and you say, I hear a band playing music. Gestalt is also something that's our sense of smell, that we do with our sense of smell. For example, if you smell the smell of baking bread, and the smell of garlic, and the smell of tomato sauce, and you smell the smell of cheese, and the smell of pepperoni, chances are you're not going to identify all those individual smells, but rather you're more than likely going to say, I smell pizza. So the smell is another area in which we can use this Gestalt, where we sort of pull everything together into an organized, meaningful whole. Of course, touch is the same. If someone's touching you on the front and the back and the shoulders all at the same time, you probably don't recognize that as being separate things. You probably recognize it as being a hug or an embrace, one single thing. That's the idea of Gestalt. Let's look at some more Gestalt principles. Next slide. Closure is not the only Gestalt principle. There are several other Gestalt principles, and let's cover a few of them. Look at these figures. Looking at the top left figure, do you perceive 6 separate lines, or do you perceive 3 columns or 3 bars? Most people will perceive 3 columns or bars. The reason is that our brain naturally takes objects which are closer to each other and associates them. So this is the principle of proximity. Things that are close we associate. For example, you may assume that roommates, 2 college roommates, are closer than they actually are in terms of their values or their views or their beliefs, simply because they're in physical closeness or physical proximity to each other. Looking at the top right figure, if we ask people what do they see here, Most people will report, I see three columns. I see a column of triangles, a column of circles, and another column of triangles. Why? Because our brain tends to group things in terms of how similar they are to each other. Another Gestalt principle at the bottom left is continuity. This looks like, most people will say, looks like a straight line that has a curved line crisscrossing it. However, we could take half circle figures and put them and arrange them like that to where we have half circle figures next to each other and that create this illusion of continuity. Finally, on the bottom right, connectedness. Most people will say that they see three dumbbell sorts of shapes, or three maybe weight sorts of shapes, rather than I see 6 dots and 3 lines. So we connect, our brain naturally tends to connect things that we see in our environment. All these are perceptual principles that happen without us even having to think about them. Next. Think about the Mona Lisa painting. How would you describe the Mona Lisa painting? Before you go on to the next slide, write down for yourself a few things that you recall about the Mona Lisa painting. In case you don't remember the Mona Lisa was painted by Leonardo da Vinci, and it's a portrait of a single female, and typically what's noticed about it is she has kind of a mysterious smile. So remember whatever you can about the Mona Lisa before going on to the next slide. Next. So what did you remember? Did you say anything about the smile or the eyes? Did you say anything about the hair color or the clothing or the posture? What did you remember? Most people remember something about the actual person herself. Typically, when asked about the Mona Lisa, most people will not tell you about the background in the picture. Now, why is that? As we look at the background, there's some interesting things. It looks like there's perhaps a road on the left or some kind of water on the left. On the right, there's some very interesting looking shapes. And some people even suggest that the left and the right halves of the picture don't match up. So why do people, with such a fascinating background, why do people spend so much time looking at the figure of the woman? The reason is that we have a key perceptual principle called figure-ground organization that our brain automatically does to help us understand the sensations coming in from the environment. Next slide. To illustrate figure-ground, here's a couple of questions. You're talking with someone at a noisy party. Why can you hear someone else say your name? It's noisy, but all of a sudden someone says your name and you hear it immediately, even though your attention was elsewhere. Why does your name stand out above the general bustle or conversation in a crowd? Second question, how does your tongue know when you have food stuck in your teeth? You know how it is. You get food stuck in your teeth and your tongue continues to work and work and work at it to try and get it out. How does your tongue know that? Both of these have to do with the principle of figure-ground organization. It is a principle of perception. We automatically notice what stands out and ignore the background. This is the idea of figure-ground. Now, the important thing about figure-ground is that we have to be able to pick out what is important and what is not. So if you walk into a room and the only other person in the room is a large, rather scary-looking guy, are you going to focus on the guy, or are you going to focus on the wall behind the guy? Chances are you're going to focus on the guy. Why? Because it's important for your survival. Figure-ground is the process by which our brain automatically perceives and organizes our world into what's important and relegates everything else into the background. Let's take a look at this on the next slide. So what do you see here? Some people will say, they look at this and they say, I see a black background with white arrows. Some of the white arrows are pointing upwards to the right. Some of the white arrows are pointing downwards to the left. Other people will look at it and they'll say, oh, I see the figure of men walking. Looks like they're walking downstairs. and each one has an arm on the other one's shoulder. What you see depends in part on what your brain calls the figure and what your brain relegates to the ground or the background. So for example, when you're looking at the picture as white arrows, what your brain does is it relegates the black to the background, and you don't really see the men. What you see is arrows going up and down. When you're focusing on the men as the figures, the white becomes the background, and the white arrows become nothing more than what is left over, the in-between spaces between the men's arms and legs and bodies. Next picture. Next slide. Here we have an interesting illustration of figure and ground. What is the figure here? People look at this and they'll say, the man on the horse with the other horse is the figure. But suddenly something leaps out to them. Just to the right of the red horse, the rocks and the water make a face. And then suddenly they see that above the man there's a face in the trees, and above the red horse there's another face, and to the top right the tree branches form a face, and to the left of the white horse there's a face, actually two faces. Look at the slide for a little bit here and see how many faces you can find. All of these faces started off as being the ground, didn't they? They were the background, while the man on the horses were the figure. But suddenly, as we see these faces sort of leap into our perception, the faces made out of stones and rocks and trees become figures themselves, and other parts of the painting become the background. A fascinating painting, to be sure. Next picture. Alright, here's an interesting trick for you. It's called the floating finger sausage trick. Hold your fingers about a foot from your face and look past your fingers, that is, look off into the distance. Move your fingers from about 3 inches apart to gradually become closer and closer together. Keep looking in the distance. The trick won't work if you look at your fingers. It will only work if you look in the distance. If you keep looking in the distance, as you bring your fingers closer and closer together, you'll see what looks like a little floating finger sausage, just as is shown in the diagram above the man. How can this be? Why is it that we can have a little sort of finger that's cut off from both sides of our hands that floats off in front of our face? The reason for this has to do with principles of depth perception. Depth perception is our next topic. Next slide. Depth perception is the ability to see depth, and there are two methods by which we can see depth. One method involves binocular cues. Binoculars is a familiar word. Binoculars is a sort of a looking glass that has a place for both eyes to look at the same time. The reason that we call them binoculars is because both eyes are used. Binocular depth perception cues are cues in which we need both of our eyes to see depth. So, an example of this is what is called retinal disparity, or just disparity. In other words, each eye looks from a slightly different angle. Your right eye and your left eye see slightly different views of the world. If you want an illustration of this, close your left eye, hold up your right eye, keep your right eye open, hold up your thumb, and cover up something in the distance with your thumb, maybe something across the room, a calendar or a window or something like that. Okay, you got it covered up with your thumb. Now, without moving your thumb, switch eyes. Open your left and close your right. And what you'll see is you have a different picture. Whatever you covered up with your thumb should now be visible, and almost as if you had moved your thumb quickly to the right. However, you didn't move your thumb, you know you didn't. Why is this happening? Because you have a slight disparity between what each of your eyes sees. Each eye sends its own separate message to the brain, and as we mentioned in the last lecture, the part of the brain that's responsible for processing visual depth takes both pictures, the picture from your right eye and your left eye, and blends them together into one single cue, or one single picture. A second binocular cue for depth perception has to do with your eye muscles. Cross your eyes for just a moment. Don't worry. What your grandmother told you about your eyes sticking that way isn't going to happen. Go ahead and cross them for a moment. Do you feel the strain on the muscles in your eyes? This is because the muscles that move our eyes have nerves, sensory nerves built into them, and our brain receives information about the tension within our eye muscles. And so your brain senses whether your eyes are converging, whether they're looking close or whether they're looking far away. It senses how much effort the muscles are using to make your eyes look close or look far away. And this sensation of your eye muscles is something the brain can also interpret as depth. So when you're looking far away, your brain will interpret the relaxation of those muscles as that you're looking far away. You're looking at something distant. When you're looking at something very close, almost immediately in front of your face, the tension of the muscles that pulls your eyes inward to focus on it, your brain also senses those tension feelings and gives you a sensation of how close the object is. But there are also cues that are called monocular depth perception cues, meaning that only one eye is needed. Can you imagine being a major league umpire with only one eye? You know the usual question that a baseball manager has for an umpire. What, are you blind? Well, could you imagine being an umpire with only one eye? There's a real life umpire named Max McCleary who has only one eye. And he's able to work as a baseball umpire. And the reason is that he uses monocular cues rather than binocular cues to help him perceive depth. Let's look at some of these monocular cues. Next. As you look at this picture, if you're like most people, you'll say, yeah, I can see depth in this picture or this painting. What kinds of things allow you to see depth here? Well, for one thing, the people who are close up, or the people who are at the bottom of the picture, are much larger than the people who are up towards the top of the picture. So our brain interprets that relative size, the size of the people close, the larger people, as meaning that the people are closer to us. So relative size, bigger equals closer, is one of the ways through which we perceive depth. And we can do it with one eye or with two eyes. Another cue is that the houses that we perceive as closer block the houses that we perceive as being farther away. So the closest house on your right actually blocks off your view of the next closest house, and so on and so forth all the way down the line, each house blocking the one that appears to be farther away. The word for this is interposition. Closer objects blocking out farther objects is something we see on our everyday world, and our brain comes to interpret that as anything that blocks something else out means that the thing that is doing the blocking is closer, and the thing that's being blocked is further away. Finally, if you take a look at the picture here, you'll see that on the left-hand side, you've got a river or a canal that seems to move up towards, from the side of the picture up towards the center of the picture. In the same way, the row of houses seems to move from the side of the picture up towards the center of the picture. And we have in the middle of the picture a point where these perspectives seem to kind of meet. This is called linear perspective. When we see lines coming together or converging, our brain automatically interprets that area where they come together as being farther away. Even if it really isn't farther away, we still interpret it as being that way. Next. So here's our monocular cues. Relative size. Things that are bigger our brain interprets as being closer. Interposition. When we see objects blocking other objects, we interpret the closer objects as the objects that are blocking as being closer. So we see closer objects blocking farther ones. And then finally, linear perspective. When we see lines converging together, our brain perceives that as meaning farther away. The interesting thing about monocular cues is that they give us some very interesting optical illusions. Our brain perceives things that really aren't there. We'll take a look at a few of these on the next few slides. Which red bar is longer in this picture? Well, if you take a ruler, you'll find that neither. They're the same size. But which red bar appears to be, do you perceive as being bigger? People uniformly look at this and perceive the top bar as being longer. Now, why would this be? Well, because we have linear perspective here. We have actually several lines. We have the lines of each side of the road coming together. We have the center line of the road coming together up at the top of the picture. We have the lines of the horizon coming together at the top of the picture. All of these lines coming together suggest to our brain that we have distance in this picture. We have depth. And with the red bar on the top being placed up closer to the place where these lines are converging, our brain automatically processes it as being bigger, even though it isn't bigger. So again, that's one of the ways in which our brain can be fooled. Another piece that we didn't talk about is that objects that are higher up in a picture tend to be interpreted as larger as well. And this adds to that illusion that the top bar is larger. Oh, here's an interesting picture. One time in an intro psych class, I asked students about this. I said, what do you see here? And one young lady said, "Oh my goodness, it's a big monster and he's chasing the little monster, and the big monster is mad and the little monster is afraid." She went quite a bit beyond sensation. If you look at this picture, it does appear that the monster, the higher up monster, is larger than the lower monster. But take a ruler out and measure them on your screen, and what you'll find is that they are the same size. So why does it appear that the higher one is larger? Well, in part because of that linear perspective. We have all the lines converging in the tunnel and in the floor of the tunnel, and it looks like they're coming together at a point in the distance, and that's where we find this monster. And so he looks much larger to us. The one in the foreground isn't as high up in the picture, and he's closer up, farther away from that convergence point, so he looks smaller. Now, what about this? The whole thing of seeing the one in front as being afraid and the one in back as being angry? That's a little twist that our brain could put on this. If we interpret or if we perceive one object as bigger and chasing a smaller object, even though they're the exact same picture, we might actually interpret emotional content to this picture as well. Next, here's a fascinating illusion, and what you'll need is a ruler here to check this out. This is one of the more amazing ones that I've seen. As we look at these two tabletops, believe it or not, the tabletops are exactly the same size. Now, it's hard to believe because the right one looks like it's wider and the left one looks like it's longer. But once again, what we have here is an optical illusion in which these monocular depth cues are giving us a story about something that isn't actually true. Because the one that is the table on the left is a little higher in the picture, and the one on the right is a little lower, our brain takes that and we perceive the one on the left as being longer than the one on the right. However, when you get out your ruler and measure them, you'll find that they're exactly the same. It's a fun little illusion. Next slide. Have you ever seen a funhouse sort of room like this? Very interesting sort of thing. It's a room in which two people are able to stand, and another person, where the red arrow is able to peek through a peephole at the two people that are in the room. But the room is created in a special fashion such that the back wall on the right-hand side is actually closer to the person who's viewing through the peephole than the wall is on the left-hand side. And so what happens is we get an illusion, even though it looks like, when you look through the peephole, it looks like the room is in a perfectly rectangular fashion. It actually is not. And so the girl on the right-hand side will appear to be much taller than the girl on the left-hand side, even though they're the same size. Take a look at the next slide and you get a picture of what it looks like through the peephole. Here we go. You see how we're lacking, the room is created such that we're lacking the cues, the monocular cues that would allow us to notice the depth, to notice that the girl on the left is farther away than the girl on the right. Interestingly, in this sort of funhouse room, if you were to have these girls switch places, it would look like they were growing, the girl on the left was growing in size and the girl on the right was shrinking in size as they switched places. And you could watch that happen before your very eyes, because the depth perception cues, the monocular cues we rely on, are so distorted in this picture. Next slide. All right, look at this picture here. You have a picture of a female's face. Go on to the next slide and look at the picture there. Do you see similarity? Chances are you can still see the woman's face, but now you see a man playing a saxophone with a little bird in front. And go ahead and look at the next slide. What if we show the picture on the right, the picture of the lady's face, to a group of people, and then show them the center picture? What do you think they're likely to see? They're likely to see the woman's face again. What if we show first a group of people, we show them the man with the saxophone, the picture on the left, and then show the center picture? What will they say they see? They'll say that they perceive a man with a saxophone. This illustrates that in part, what we perceive depends on what we expect to perceive. This is called perceptual set. Our mental expectations influence what we perceive. I remember a time driving home from work about 1 in the morning when I was a teenager, and driving through a narrow road that went through a woods area. And as I was driving along, very tired, all of a sudden I saw a bear. And I started up and was very startled by this and looked, and sure enough, it was actually not a bear. It was actually some stumps that were just tree stumps by the side of the road. But I had interpreted it as a bear. I perceived a bear in part because of my expectations of driving alone at night through the woods and it being a little bit of a creepy place. So mental expectations do influence what we perceive. And this will be clear in some of the next few slides. Next slide. What do you see here? What is this? Well, given the grainy nature of the photo and the black and white and the lake effect, most people look at this and they say, oh, Loch Ness Monster. Immediately say, Loch Ness Monster. However, as we look at this, we would expect that an object like a large object like a sea creature that was in the water would be creating ripples, but we don't see that here. What we see is no ripples at all around it. We see just the uniform waves of the lake. The reason being that this is a piece of driftwood. However, because of our perceptual set, because we've seen photos, grainy photos that look like this before, and we've seen labels that say it's pictures of the Loch Ness Monster, our perceptual set is such that we immediately say, ah, Loch Ness Monster, even though the evidence, when we really think about it, the evidence doesn't support that. Next slide. How about this? What does this look like? Most people will look at this and immediately say, ah, UFOs. However, when we look carefully, we find that they're actually just cloud formations. Now, they're very bizarre cloud formations, unusual cloud formations, but because they're over a city and because they're round, our perceptual set would say to us, ah, I perceive UFOs. If you don't believe they're clouds, go on to the next slide. If you type in cloud UFOs and do a Google search on that, you'll find some sites that have some amazing pictures of clouds. Clouds that look very much like they might be UFOs, but are pretty clearly real cloud pictures. Pretty neat stuff. Next slide. Oh, what's happening here? A mother's reaching out her hands to have a baby walk right off the edge of a table? Or crawl right off the edge of a table? Actually, what this is a unique, ingenious device called a visual cliff. And the idea of the visual cliff is to be able to determine when babies develop depth perception. The way that it's set up is that the baby's hands are actually, right now, are actually on glass. So the baby is placed on a table that has that checkerboard pattern, and there's a glass front that to the table that comes across to where the mother is, and below where the table ends and down below there's the same pattern of tablecloth. So for the baby it appears that there's a drop-off. So visually it looks like a cliff. Now a baby that's young, that's not yet developed its depth perception completely, will crawl right across the glass to the mother because it doesn't perceive the depth there. However, a little bit older baby who's begun to develop depth perception won't crawl out onto the glass. What it will do is it'll look at mother and look down at what appears to be a drop-off, and it will start crying, and it will not go over the edge because it doesn't want to fall off the table. So this is a good way to gauge, before a baby can even speak, to gauge when it's developed its depth perception. Next slide. When do we develop depth perception? At 3 months, it's clear that we have developed some of those Gestalt principles that I've told you about already. 6 to 14 months is when we develop depth perception. When a baby, somewhere between 6 and 14 months, when the baby recognizes that there appears to be a cliff there. But it's possible that perception may be a lifelong learning process. And I'll leave you with a quick story about a fellow by the name of Colin Turnbull, an anthropologist who was studying pygmy tribes in Africa. And he wanted to go from one forest tribe to another forest tribe, and so he invited one of the young men of a tribe to go with him. And when they drove out onto the plain, this young man, who had never been out of the forest, began to notice some very strange things. For example, he noticed that buffalo off in the distance were tiny, and he thought that they were insects because they seemed so far away. He had never gained that long-distance depth perception, or that idea that things that are farther away are smaller, because the young man lived in the forest where you could not see very far. But once he got out onto the plains, he found that the world was very different than he had thought that it was. And in fact, he found it very spooky and frightening, the idea that things as large as buffalo could look as small as insects when they're far away. So even though this young man found this very unnerving throughout that day as he traveled with Colin Turnbull, the anthropologist, this young man was able to develop the ability to understand some of these monocular depth cues. And so what we find is that some aspects of perception seem to be a lifelong learning process, and it doesn't seem to be too late to learn some of these processes even later in life. End of slides.